everyone, welcome to another math club talk. Today we have Siddharto Das, who is a B.Math second year student. He is interested in analysis and topology. Today we will be giving a talk on filters. Over to you, Siddharto.
Thank you, Gaurav. We will start with two basic rules which are motivating. First rule, I will take two sequences. In the real numbers such that x converges to x and y converges to y. And I have proved that the limit of the sum is the sum of the elements. So, there exists the epsilon greater than 0. There exists n1 y minus y epsilon away from y for every n greater than n2 and take n as the maximum of n1 and n2. Then for n greater than equals to n, we have xn plus y minus x plus y by triangle inequality. And then by using these two conditions, we have this epsilon plus 2, epsilon plus 2, which is epsilon, and which just shows that the second proof is almost identical. So this time I have two functions f and g from an interval I to R and C a cluster point curve means every open, which means that every open interval about C has a logit intersection with I. And I let limit x goes to C f of x be A, and the limit x goes to C g of x be B. This means that there is a delta 1 greater than 0 such that f of x minus A is less than epsilon of A. Epsilon greater than 0 is less than epsilon for every x away, delta 1 away from C. There is a delta 2 greater than 0 such that g of x minus B delta 2. What we will do is we will take a delta as the minimum, delta 2, and then use the same thing. Or we have f plus bx minus a plus b by triangle inequality x minus a is gx minus b, and this is strictly less than epsilon plus 2 plus epsilon 2 is equal to epsilon this shows the limit as x goes to c, f plus g of x is equals to a plus b. Right. And these two proofs are, well, identical except for some minor details. So what you have is, suppose I have a condition such as this, xn minus x is less than epsilon by 2. I am looking for regions where this condition holds true. So these must hold true for at least regions like this and this. It's even better if it holds for larger regions, and if it holds for like two regions like this, I need to be able to take intersections of those two regions. And of course, I need that such a condition to hold in a non-empty region. So I will just collect all these conditions into one structure, which I will call a filter. So filter definition of filter f on a set x is the subset of the power set of x such that the following could be 1 if there is a subset B of x, which in turn contains a subset A of x, which is a part of it, then B is also in it. Second, any finite intersection of sets in F is also in F. And third, that the empty set is not in F. Like paralleling what we need for limits to be well defined. So this is how we will try to justify limits over the real line, limits for sequences. And we will also, so this is like things what you will need on the domain side, and on the codomain side you will need a topology. So I will define a topology. So a topology on a set X is the map from X to power set of X. Such that again the following rule. So this B is what we call the neighborhoods of B of X. And x for x, a point in x, we will call B of x the neighborhoods of x. So, first, again, if a subset B contains a neighborhood of x, then B is also a neighborhood of x. Next, finite intersection of neighborhoods neighborhoods of x is also a neighborhood of x. Number 3, x is in every neighborhood of x. for like the normality, we will have a normality condition. If V is a neighborhood of X, then there exists a W neighborhood of X such that V is a neighborhood of Y for every Y in W. So this is what we mean by topology. And what do we observe? Note that 1, 2 and 3 correspond exactly to 1, 2 and 3 there. Right. So what we have in effect then is define the filter the neighborhood filter for every point x and x. Right. And for a familiar example, what is the topology on R1? So the topology in R1 is just B of X is the set of supersets of open intervals about X in R. So for what you are doing, you are considering V of X consists of all sets which contain a set of the form x minus delta to x plus delta. And this is a general technique to generate filters. So what you are trying to do is you are first you fix that these must be in the filter, and then you are completing the filter to satisfy all these properties. So this is a general technique, and what we need, suppose we are given a set of a set S of subsets of X, which we need to include in a filter. Necessarily, this must not be less, and any finite intersection of sets in S is also in S. 1 and 2 and 3, and as long as S itself is not empty, this is sufficient. So what you do is you take B as the set of finite intersections of sets in S, and what is the filter is just the set of supersets of sets in B. And we call a set like this a subbase. A set like this a base of a filter. you can verify that this is a filter. And what we had here was that these sets form the base for this neighborhood filter. Okay. And B must be part of it just using the conditions I listed earlier, and F followed necessarily from condition 1. This is in fact the smallest filter you can have that contains S. So an important example of filter construct is this way is the Fresh filter on F. So the basis all sets of this form for every NNN. And you may recognize that this is what is fundamental to every limit argument we use for sequences. And I will also use a terminology that F1 is finer than F2 if F1 contains F2. And I will also talk about bases being finer than other bases, in which case I just mean that the filter generated by the first base is finer than the filter generated by the second base. Right. And talking of sets becoming filters, we can talk of combining filters if that's possible. Take all the sets into filters and make a new filter out of them. So what do we do? So I will just write it here. Suppose I have a family of filters Fi. And then there is a filter F on X that is final. Then every filter in that family can only every finite intersection of the forms is non-empty, where J is a subset of I, which is finite. J is finite, and AJ is a set taken from the filter Fj. And this warrants no further proof because it's just clear from the discussion we had. Every finite intersection of the sets collected from Fi looks like this. The corollary corollaries are interesting. So every G in F is the set of filters on X every G in F has an upper bound. The proof is simple. So suppose I have a chain. I look for intersections of this problem. Right. So this is a finite subset of this value. So this has a maximum element. By maximum I mean I have an element fd which is finite, then fj for every j in j and k is from capital J. Right. So in fact what happens is every one of these AJs actually comes from fk. So by the second condition of filters, this is also a set in fk, and since this is a set in fk, this is non-empty and limit. So there is only one thing left to do. If f is the filter on X, there is a maximal filter. U on X, that is finite then. Again, there is nothing to do in this proof apart from applying Zorn's lemma. And we define U is an ultra filter on X. So for every filter F on X, I have an ultra filter finite. So like why did I bring ultra filters into this? First of all, they came naturally from the structure filter. Second of all, there are two important relations that ultra filters have with filters which make it easy to replace any theorem of filters with a theorem on ultra filters. So I will just write the theorems. The first is that a filter F on X is an ultra filter if and only if for every A a subset of X either A is part of U or is a form of transfinite inversion you can do. So suppose you start with the filter f on x, you look at subsets of x that may belong to the filter f. You may include it with the filter f using so suppose you look at a subset A, either subset A has non-empty intersections with each set in U, or a complement has non-empty intersections with each set in F. Then you put A or a complement as needed with F and you get a new filter. Then you go on like this, but we will not do that here. That's the intuition we will use the simpler tool there. This will first. Suppose A is in U or a complement is in U for every A subset of it. And suppose U is not an interpreter. At that theorem we have then there is a U prime ultrafilter finer than U. Finer than U, which finer than U, and string since is strictly finer than U is not U prime is not U. So there is a in U prime and A is not in U. Since A is not in U, a complement must be in U. Because of this. And since A complement is in U, A complement must also be in U prime. But A complement in A have empty intersection, which is not possible. So this is the point. Now suppose U is an ultrafilter and say that A is not in U as well as A complement is not in U for some subset A of X. Okay. A cannot be empty, first of all. A cannot be X. Because X is in every ultrafilter. Because X is in every ultrafilter, so or any filter in fact. And X, and for the same reason, if A would have been empty, then A complement would be X. And then again. That's not possible. Take any B in U. A complement intersection with U must be non-empty. Otherwise, if A complement intersection B is empty, then A is in fact a superset of B, which must mean that A is in. So, since this is true for every B, that means that you can. So there is a filter then U, which also contains a complement. But A was an ultra filter, it was maximum. So it's not possible. Yeah. And the second theorem, for the second theorem, you need to first verify that any intersection of filters, any arbitrary intersection of filters is also a filter. F is the intersection of every ultra filter final, then F. F is a filter element. So I call this intersection of every ultra filter final then G. And G is clearly final element. If it is strictly final, then we have A in G and A that is not in it. Again, we have the same proof technique. A complement intersected with B for every V in F must be non-empty. So there is an ultra higher than F, say U, which contains A complement. Now U contains A complement, then U cannot contain A. But this is this is a contradiction, since then it can't also be in G. Get on. Talk more about prerequisites. Ask me to verify the following. Not very difficult. B is a filter base on X given on negative. B is not empty. The empty set is not in B. And second, if B in B find an intersection of sets in B, there is a U in B which is contained in B. So that B can be a part of the filter that is in B. And this is also easy. If B is a filter base on X, if a function from X to Y, then f of B, which I mean f of for every X and B is the filter base on X. But it is follows this. Now finally we can talk about it. We take X a topological space. By topological space, I simply mean a space set with a topology. Definition: A in X is a limit point of X with limit point of X with respect to F, a filter on if and only if F is finer than the neighborhood filter of A. Right? And I will need an auxiliary definition for it. So, the closure of A is simply all points X and S for A a subset of X, such that A intersection B is non-empty for all B, for all neighborhoods B. So then I will be able to have a generalization of limit. So A on X is a cluster point of X with respect to a filter F on X if and only if A belongs to the closure of V for every element V from the filter F. What does that mean? That means that every neighborhood of A has a non-empty intersection with every element V of it. And this meant that every neighborhood is contained in every neighborhood is a part of. Some very simple things to know. If A is the limit point with respect to F, then A is obviously a limit point with respect to any filter G which is final line. And since this is the case, every neighborhood of A has a non-empty intersection with every element F of every element V of F, then I can have a filter that is finer than both F and the neighborhood filter of A. So I have A in X is the cluster point of F, and if and only if there is a filter G that is finer than F and V of X, which just means that G is a filter finer than F which converges to F. But ultra filters don't have any filters that are finer than strictly finer than that ultra filter, which means that if A is a cluster point of an ultra filter, then A is also a limit point of that ultra filter. I won't try to discuss. Important example. We should return to sequences. for a sequence xn in x, xn in x, and define the function that represents the sequence. It takes n to xn. Then generated by f of b. What is b? Where b is the restated filter. Is called an elementary filter due to expansion on it. What does this filter, elementary filter consist of? This consists of all subsets of it that have all but finitely many elements from the sequence itself. Which means the RA1, the reanalysis definition of limit of the sequence is compatible with this basic. The limit point of this elementary filter. This is slightly misleading because for arbitrary topological spaces this limit may not be unique, but for real spaces this is unique. Similarly, you can have cluster points of a sequence which match with the limit points of a sequence which we call the system. So this cluster points of this elementary filter. And R is special in the sense that you can have a countable base for any neighborhood filter. For example, so the neighborhood filter of X is generated by sets of this one. This forms a base for the neighborhood filter of X in R1. So every neighborhood has a countable base, which ultimately leads to this filter. If f is a filter with a countable base, then f is the intersection of every elementary filter finally. Finally, then. And I urge you to check when you prove that when you prove that limit x goes to c f of x is equals to a if and only if limit n goes to infinity f of x n equals to a for all x n x n goes to c. When you prove this, that where did you use this theorem? limits don't change. Let an or n actually be a base of x. Then being defined by Bn intersection of j and j goes to 1 to n of an is also a base of how? Okay. Clearly, every Bn is contained in An. Also, since An is a filter base, I asked you to verify something ago that any finite intersection of elements in An must contain an AK for some An. So, An is also contained in some Bk. So, the filter generated by Bn is finer than the filter generated by An, and the filter generated by An is finer than the filter generated by Bn, which means they are the same filter. Let G be the intersection of elementary filters finer than F. If G is strictly finite, then there is a K in G which is not in F. Then same technique. Bn is non-empty. The intersection of A component Bn is non-empty for all n. Then I can have an Xn which is contained in Bn, and this elementary filter is clearly finer than the filter Bn, because this is a decreasing sequence. So this is the elementary filter due to this is finer than the filter generated by Bn. But this filter contains A complement. This filter contains A complement. So this elementary filter can't have A as well, which means A can't be in the intersection G, which is a contradiction in reality. Similarly to the function we have here, we can do a similar construction for any arbitrary function on X. So I can talk of unit points of a function. Let it be a function from X to Y, X topological space. F a filter on X. If and only if Y is the limit point of this filter. F is a filter, so it's also a filter case. This is also a filter case. And by a limit point of filter case, I just mean by a limit point of filter limited by filter case. Similarly, I can define what is the just point. I'm going to write this one. And in this special case, when this f is in fact the neighborhoods of a function, a point A or A in X, we write limit x goes to A, x. Again, this y may not be unique, so this notation will be misleading. For reals, there is a reason why it should be unique. And I will end with some definitions which ask you to ponder. Let f be a function, let f be a function from x to y, x and y both topological spaces. Then I define f to be continuous. F is continuous at A and X. X goes to A, f of x is in fact f of x. What does this mean? Every neighborhood of f of a contains a set of this form where v is the neighborhood of x, which in reality, what does that mean? Is that a this contains the set of this form. Which is the definition of continuity? But this is not the ordinary element you see in real analysis. Since B's, the neighborhoods of A still contain, I need, in fact, this here which is not. That can be fixed if A is a non-isolated point. Okay. By which I just mean that every neighborhood of x has a non-empty intersection with x complement. Then the trace of the neighborhood filter that is this set F intersections of the neighborhood of x with x complement this is also a filter. Otherwise, what you would have is an empty set in the set which won't allow it to be a filter. In this case, so F is a filter on X complement. So instead of writing this, I will just write limit x goes to a, x is not a, f. And then I have here, with all these assumptions are a, f is continuous at a in x is an only. Limit x goes to a, x is not a, f of x is equals to f of a, which follows our chain from the definitions. A final remark, filters can be used to state topological properties very succinctly. For example, a Hausdorff space is simply a space where every filter has no more than one limit point, no more than one cluster point. A quasi-compact space is one where every filter must have at least one cluster point, and a compact space is just a Hausdorff and a compact space, and which makes the proof of, say, Tikhonov's theorem just trivial. It just means that the limit in a product topology is seen as taking the limits component wise. And that's all. Thank you.
Are there any questions for the speaker? If not, then let us thank the speaker once again.